My name's Erich Elsen, and my partner Vishal's in the back. And this project actually started as some work that we were doing for Ion Torrent, who just presented right before us, as one of the later stages to the pipeline that they talked about, where you need to actually align the DNA sequences that you find using their sequencing machine. So first, I just wanted to give a brief overview of the problem in case anyone here isn't familiar with what we're trying to do. It'll be quick, so if you... I don't know what's going on here. But if you already know what's going on, then hopefully you won't be bored in the 5 minutes that it takes to go over this. So basically, if we have two DNA sequences and we're trying to align them to one another, basically we want to make them match up as close as we can, while taking into account the fact that there may be swaps between the two sequences or insertions or deletions between them. And the way that we do this is we assign scores to each one of the... Whoa, what's going on here? That's really weird. All right. Sorry about that. So the way we do that is we assign scores to each one of the operations that can occur. So for example, if there's an insertion or a deletion, we might give that a score of -2. And then for each one of the symbols, we create a table and we can assign a score to each insertion, or to each pair of symbols that we have individually. And in general, we can leave this as a table that has sort of n squared entries, where n is the number of symbols in our alphabet. So for DNA, we have 4 symbols. So this table could be up to 16 in size. And for amino acid sequences, it's usually actually represented as a table. But for DNA sequences, most of the time what we do is we simply contract this table down to 2 values, one for when there's a match, so the diagonal, which is usually a 1, and 1 for the off-diagonal entries when there's a mismatch, and that's usually a score like -3. So usually when we're doing DNA alignment, this table becomes actually just 2 values. And then, so this is the scoring for the original Smith-Waterman algorithm. But it turns out that when we, to really score biologically accurately, we need to do something a bit differently. And what we want to do is penalize when we start a gap. So when we either create an insertion or a deletion, we want to penalize this more heavily than just extending a gap. And one of the reasons for this, for example, is because DNA codes for amino acids in triplets. If we were, for example, to just mutate one of the base pairs, then we'll get one amino acid wrong. And obviously that's not good, but it's not nearly as bad as if we insert a gap and sort of just shift everything down by 1, because then we've probably screwed up a whole bunch of amino acids, not just one. So we want to penalize starting a gap pretty heavily. And so this actually leads to a slightly different scoring and algorithm. The algorithm is now actually called the Goto algorithm. It's no longer the Smith-Waterman algorithm. Unfortunately, Smith and Waterman get all the credit, even though really Goto is the algorithm that everyone tends to use. But basically the idea here is that, so now we have 2 scores. We have a score for opening a gap and then a score for extending the gap. And so the algorithm, the Goto algorithm, is what we end up using. And basically it's a recurrence relation with 3 values per cell. And the basic idea is, we line up one sequence along the columns, one sequence along the rows, and then we have a matrix that's of size m times n that we need to fill in according to these equations. And the basic data dependency, I'm not expecting you to read these equations right now, but basically the data dependency is if we're trying to fill in this cell, we depend on the 3 cells to the top, upper left, and left. And the calculation basically proceeds from there as we fill in the matrix. And the goal is to find, using this, we find the alignment that has the highest score, the cell that has the highest score. And using that, we can figure out what is the best alignment between these 2 sequences. So this ties into the, for example, DNA sequence machines, and specifically the Ion Torrent DNA sequencing machines, in that, as was mentioned in the earlier talk, for example, the Proton 2 chip has 660 million wells, and each one of those wells is producing a base read that can be anywhere from 35 to 400, or I think really they're hoping for even longer than that. So some very long reads. And each one of these reads needs to be aligned to, ideally the human genome. So that's a whole lot of alignment that we need to do, and this is actually, a quadratic algorithm. It's order mn. So this is a great deal of work that we need to do to align these sequences. So specifically, the way this works is that for each sequence that we read off the machine, a heuristic aligner will generate 20 to 50 possible candidate sequence matches. So we're not using Smith-Waterman to align each sequence to the entire human genome. We'll use something that's faster and less exact to create possible matches, and then we'll use the Smith-Waterman algorithm to find the best match amongst those possible candidates. So what this amounts to then is we have millions upon millions of independent alignment problems that are of size somewhere between about usually 16 and 1,024. It's not a limitation of the algorithm. I mean, we could go bigger. That's just the longest reads that we get off of the chip. So, and the other important thing is because we're evaluating, so for example, we're aligning one read that we get off the chip to 20 to 50 possible candidate sequences, we only need to compute the score first. So obviously, when we compute an alignment, we want to be able to figure out how do the sequences actually align. I mean, that's really what we want to know. But the first thing is, it turns out that it's much more expensive to compute the actual alignment compared to just the score of the alignment. So when we're computing first all of the matches, we compute only the score. We figure out which of the candidates was the best match, and then we can go back and actually compute how do they line up, because that's much more expensive, so we want to minimize the amount of time that we do that. So the basic strategy that we're going to take is, since we have so many problems, is to parallelize across the problems. It's, another common approach people take especially when they have bigger alignment problems that they want to solve, is they will try to parallelize within a problem, and you usually do that by moving along a diagonal. So it turns out for us, since we have so many problems to solve, and they're all relatively close to the same size, that it's much more efficient to just solve them within each thread, and that way we never need to worry about communicating between threads, which tends to slow you down. So that's the basic approach we're going to take here. Another basic, just upfront thing that we're going to do is we can afford to sort the problems by length to minimize any sort of divergence that's going to happen when we're doing the solution. Let's say we're solving 100,000 problems at a time. Well, sorting 100,000 numbers is basically of zero cost compared to performing 100,000 alignments. It doesn't matter at all. So it's definitely a worthwhile optimization step. And along with that, I guess another important thing is we stride out the sequences in memory, so that so for example, if for each problem the sequences were contiguous in memory, then we would have to somehow cooperatively load the sequences into shared memory and then transpose them to get them into the threads. That, of course, it slows you down. It takes up shared memory. It might hurt your occupancy. And, I mean, you want to avoid it if you can. And again, for the same reason as that we can sort, solving the alignment problems takes so long that reordering how the base pairs are stored in memory is, again, basically a no-op. So it's very much worth it to do that to avoid having to do any sort of communication inside the warps or inside the CTAs. So, I mean, this is actually not that important when we're solving the scalar problem, but it becomes important when we're solving the vector, when we're using the vector instructions. It's, basically, since there's only 4 symbols in the alphabet, A, T, G, and C, we can compact that down to 2 bits per base pair and shove 16 of them in a word. So again, we do that up front, and basically the sorting, this compaction, and the striding all happens in one step, and it's really fast compared to solving the alignment. And I'm not really going to talk much more about it other than to mention that it happens. And so going forward, the basic strategy is, since we're solving one problem per thread, we really want to maximize how much information we keep in the registers of each thread to avoid going to memory as much as we can. This is somewhat similar to what is sometimes done in, for example, dense matrix multiplication. We put as much information in the threads as we can in the registers, and we avoid, then we can avoid communication between them, and we trade lower occupancy for very high ILP, basically. We get tons of instruction level parallelism because we're doing so much work in each thread. Okay, so let's just look at what happens when we're doing one cell update. So we want to update the cell that's in blue, and to do that we need these 3 cells that are in green. There are 3 matrices, M, V, and H, that get updated at each cell. And it turns out to update, so M, V, and H at this cell, we need M from the 3 surrounding cells, but we only need V above, and we only need H to the left. And that's easy to remember for if you H horizontal to the left, and V vertical, it comes from the top. And so basically, our idea is just we're going to go through the whole matrix, update each cell, and we just want to keep track of the largest value of M that we've seen so far, and that's the score for the problem. So if imagine that now we've updated this cell and we're going to move over and update the cell next to it, we can look at what happens. So basically this cell, we don't need information from this cell at all anymore. We calculated a value of M and H in this cell, which we're going to need to update this cell. So that works out really well. We just calculated them. They'll be in registers. We can just move over and they're still there. That's great. Let's move over one more. And we can sort of see that now this cell, we don't need its information anymore, but we're going to need the information in the red cells when we go down to this row that's right here. We need the values of M and V that are in these cells to update the row that's below us. But we no longer need the information that was in this cell anymore. So it turns out that you can basically do these updates in place as you're going across each row if you're careful not to go too far, sort of. Eventually you run out of registers. So the amount that you sort of unroll across the columns needs to be controlled. But the basic idea, let me just go one more, is that we can replace the values that were here with the new value that we calculate of M and V, and then go down the rows. And we can keep everything in registers when we do the updates like this. So let's go one more. So this is a bigger picture of what it looks like when we're updating. So we have our target sequence along the top. We have a query sequence along the side. And in each problem, we need to fill in this giant matrix. And so the basic idea is that we call the unroll factor K. And in this diagram, that I've chosen that to be 8. In practice, the fastest values tend to be 16. And actually on the K20, it's 20. It's because the K20 actually allows you to have more than 63 registers per thread. So we can actually unroll a little bit farther and get even more performance. But in any case, so the basic idea now is in a thread, we're going to, in registers, set the boundary conditions for M and V along the top. And those values will all be stored in registers. Along the left edge here, we need to load M and H from global memory, which, on the first stripe, that'll be the boundary condition, but later on it'll be what was computed over here. So we'll load the boundary condition. We've set the boundary conditions in registers, and then we can now essentially walk down the row, updating each cell, and keeping everything in registers. And then when we get to the end, we have to write out the value of M and H that we calculated to global memory so that we can read it in when we start the next stripe over here. So basically, if you look at what we've done, we've read in, this basically amounts to 1 word for M and H. And we've written out 1 word at the end of the row, and we've done, well, in reality, if this is 16, so 16, there's about 11 instructions per cup, so call it 200 instructions, and we've only moved 8 bytes in and out of memory. So that's a really good ratio. And so once we've finished a row, then we can just move down to the next row, and we load again M and H from the left. Everything is in registers above us, and we just walk down, and we can go, blast through that entire stripe, go all the way to the bottom of the column, and move very little memory around, compute the update, and then go to the next stripe and basically just repeat this process over and over again. And this works out really, really well. So it's extremely compute bound. On a C2050, which was the original target card, we get 35 GCups. So a cup is a cell update per second. So basically, when you're talking about Smith-Waterman and Needleman-Wunsch alignment problems, the general performance measurement is how many of these cells can you update per second. So that's what a cup is. And if you calculate this out, so 35 GCups, and each cell update is 11 instructions, and you calculate, well, I have 448 thread processors operating at 1.15 gigahertz. So assuming every single clock they're executing an instruction, that means actually 75% of all the instructions that got issued are doing useful cell updates, which is that's a pretty amazing ratio. And also you can look at, so basically we're using only 1/16 of the available bandwidth of the card to be able to get this performance, which is great. We have tons of room on the memory bandwidth. And looking at this, it's not very obvious how can we make this any better. 75% of instructions doing useful work is pretty amazing. So the only idea, or the only thing you can really do is start solving more than one problem per thread. So basically, for every instruction, instead of solving one problem, let's solve 2 or 4. And we can do this with these new instructions that are available on the Kepler card, which are called the vector video instructions. So first, let me just talk about what are the vector video instructions. So basically, they allow you to do SIMD, but within a word. So, normal, like SSE SIMD, you're operating across multiple words. So here the idea is within a word, we can do SIMD-type operations. So you can do 2-way operations on 16-bit values and 4-way operations on 8-bit values. The operations available to you are, the usual suspects of addition and subtraction. You can also get maximum and minimum, your comparisons, so you can do less than, greater than, not equal to. And also pretty nice is you can do averages and absolute differences. So those are quite an array of instructions that are available to you. Some other things that you can do with them. So in the simplest case, when we're doing addition, it operates exactly like you would expect. The two halves of the word get added independently. And the important thing is, if X overflows, so if we add 100 to 100 and we normally end up with a value larger than we can represent, it doesn't overflow into the next byte. It wraps around like you would expect it to if it was normal integer addition. But even nicer, if we don't want it to wrap, we can actually clamp it. So if we had signed integers and we added 100 and we were dealing with 1 byte, we added 100 to 100, instead of getting some negative number, we can just clamp it and get 127, which we actually take advantage of later on. So that's pretty nice. One other thing you can do is you can actually swizzle the operands. So swizzling is a terminology from graphics. Basically, it means we can sort of reorder the components of the byte. And then finally, the last thing that's really nice is we can do horizontal accumulation operations between the components of the word. So in this case, for example, if we imagine that we have, A and B are 2 input vectors, we can actually take the max of both halves, then add the result of those maxes together, and accumulate that with a third input operand C, and then return that as an output. So that's actually a whole lot of work that you can do with one instruction, which is pretty nice. So you're thinking, well, these instructions are great. I'd like to be able to access them. The one downside is there's not even any intrinsic support in the compiler. So the only way to get at them is if you write inline PTX. It's a little unfortunate, but it's not that hard. You just end up writing your own intrinsics, essentially, that end up looking something like this, and then you can just call them, and the compiler inlines them, and everything ends up working out just fine. I'm not going to go over this slide, but if you want to look at it online to see how you might write something like this, you can go ahead. So some micro benchmark results from looking at these instructions. You might be curious about, how fast are they? Are there differences between them? So basically, both the 2-way and the 4-way instructions have the same throughput. All of the operations have the same throughput, so whether you're doing addition, maximum, average, it's all the same. Unfortunately, they're slower than your normal integer instructions. They seem to run at about 1/3 the speed, which is a bit of a bummer, because when we first started this work, we thought we were going to get a just boom, like 4x improvement, but it didn't end up working out like that. But in any case, so they're about 1/3 the throughput. But the nice thing is that they seem to be performed by a separate hardware from the normal integer unit. So it looks like you can actually dual issue normal integer instructions and these vector instructions at the same time to get some additional instruction level parallelism. So how are we going to use this to actually, help us solve more than one problem in a thread? I mean, the basic idea is we'll just take the update equations we had before and make every operation a vector add or a vector max. And when we'll pack multiple problems within each word. And this basically works out. The question is, since each one of these vector instructions is really slow, can we avoid making some of these operations vector? That's the first question. And the second is, how do we get the scores? So like when we're comparing, in a sequence, we compare A against T and say, oh, that's a mismatch, so the score is -3. But in the other sequence, we compare T against T, and that's a match, so the score is 1. So we need to get for this add right here in this W value, we need each byte to contain the score for whether that particular sequence matched or didn't match. So it's not so obvious how to do this, and especially how to do it quickly. So the next things I'm going to talk about basically is how can we do these things, which really allows us to get good performance when we use these instructions. So we can imagine when we're trying to get the scores like I was talking about earlier, we could use the vector not equal. So I was mentioning they have comparisons. We could use the not equal operator and compare the two base, like the query base pairs and the target base pairs, and then we'll get 1s when they're different and 0s when they're the same. And then we could write some kind of loop that checks, oh, was it a 1 or was it a 0, and then moves the correct score into that part of the word. But, I mean, this ends up being quite a lot of instructions, and we already said that the vector instruction was slow, and then we're doing at least, another 8 instructions as we go through this loop. So it's really not that fast. So we want to find a better way. And the better way involves another PTX instruction called byte permute. But there is actually an intrinsic this time that you can access, although it doesn't give you access to the full power of the instruction, but it's actually all we need here. What this instruction does is really nice. It basically allows you to gather from 8 possible bytes into one word. So here there's a selection word, S, that gathers from the 8 bytes of X and Y and outputs one word. So like in this case, if the selection word, the lowest 4 nibbles, were 1, 5, 3, and 4, then in the output word, we would gather from the first location of X, then the 5th location, which is in Y, then the the 3rd location, which is in X, and then the 4th location, which is in Y. And we can generate a new word that's sort of this, permutation of the bytes of X and Y. And we can use this to generate the scores very quickly. So the way that we do this is we rearrange how we pack the base pairs in the sequences. So instead of having each sequence continue, so the colors here are representing each sequence. So for example, the red is representing, say, the first sequence. The blue is representing the second sequence, the green the third, and the black the fourth. So, and then the subscript is representing, which base pair is it from that sequence. And so we have this very weird pattern now of how the base pairs are arranged within a word. But the reason that we do it this way is so that basically, as you can see, the selection word was based upon the 4 lowest nibbles. That's what was used. So when we line up the base pairs this way, you can kind of see that I'm going to have 1 nibble for the first sequence, 1 nibble for the second, and so on. So we're actually going to have everything line up exactly how we need it to be used as the selection word in the byte permute. And then the basic idea is that when we XOR the 2 sequences, if the base pairs match and you XOR them, then you get a 0 because everything will cancel out. And if they don't match, then you're going to get 1, 2, or a 3. Exactly which one you get, I mean, it depends on how they mismatch, but it doesn't really matter, because what we're going to do, let's go to the next slide, is in the score vector, we'll put a 1 in the 0th position, and we'll put the mismatch score of -3 in all the other positions. Right? So if we have, for example, this sequence here, and we're going to XOR it, and then what we do is we mask off, so we only get the first pair of each sequence. So when they match, we have a 0. When they mismatch a 2, they match, we have a 0. They mismatch, we have a 1. And then we just, boom, use this as the selection word and gather from the score location, and then we immediately have the weights like we need them. And so this amounts to basically 3 instructions without any conditionals, and we get the weights exactly where we need them. And then the final component in basically speeding everything up is that normally in Smith-Waterman, 0 is the baseline level, and then negative, the gap open and extension scores are negative, and the weight can either be positive or negative. So what we do here is we essentially shift 0 up by the maximum negative value, which in Smith-Waterman is the gap open plus the gap extension score. And then we make the gap open and the gap extension positive. And so basically, we're subtracting positive numbers instead of adding negative numbers. And this allows us to switch some of what were vector additions into just normal integer subtractions, because we can guarantee there won't be any overflows. So this, again, gives us, since the integer instructions are a lot faster, this helps give us more speed. And since they execute in parallel with the vector instructions, it actually gives us a bit more ILP as well. So that's the basic other trick. It looks like we're running out of time. So the result then is basically, unfortunately, because the video instructions are so much slower, we only get a 5% speed up if we do the 2-way. But we get 105% speed up, so about double the speed if we use the 4-way. Now, the one downside of the 4-way instructions is that the maximum score we can represent is about 240. But it turns out that only 0.4% of all the problems out of millions end up exceeding that score. And we use the clamp that I was talking about earlier, and we just clamp to the maximum score. So at the end, we just check what alignments have the maximum score. Okay, we'll just rerun those with the 2-way, and then 0.4%, it's done really fast, and it doesn't even matter. And the end result is that on a K10, we can get 164 gigacups, and that's with the ECC on, and 120 gigacups on a K20M. And I think on a K20X, it's like 130 or 135. So in conclusion, Smith-Waterman is great for the GPU. If you shove 4 K10s into a box, you can get 640 gigacups in one box pretty easily. And in fact, if you use that server that Jensen mentioned in his keynote with 8, then you can make it over a teracup in a box, which would be pretty amazing. And actually, if the human genome is 1 billion base pairs, and we want to align a sequence of, let's say, 1,000 base pairs to the human genome, that's 1,000 times 1 billion, or a trillion cells that we need to calculate. So if we had over a teracup in a box, we could actually do an exact alignment to the human genome in less than a second, which would be pretty nice. Thanks for the talk.